Hello students, welcome to EPG Pathshala. I am Dr. Kajal Jindal from University of Delhi. Today we are going to discuss about the module Differential Equations from paper Mathematical Tools for Materials. So students, let us see what we are going to learn in this module. The importance of differential equations in engineering, physics, and other branches of science and in social sciences is described. Classification of various types of differential equations is given. Methods of solving linear first-order differential equations, both homogeneous and non-homogeneous, are described. Nonlinear equations of the separable type are described, and methods to convert some equations to separable type are described. Next, homogeneous nonlinear equations are taken up. Integrating factor that can convert some equations into exact equations is defined, and method of finding the integrating factor is given. Let me now introduce you to the differential equations. We know that the study of differential equations permeates all branches of science. Mathematics has become more and more relevant in social sciences as well. Many physical problems are concerned with relationships between changing quantities. Since rates of change are represented mathematically by derivatives, so mathematical models often involve equations relating an unknown function and one or more of its derivatives. Equations involving derivatives of an unknown function are called differential equations. Often we study situations where certain quantities vary with time. Take Newton's laws defined by F is equal to mx double dot t. This is one of the earliest examples. In this equation, if we know xt, force can be obtained by simple differentiation of the function. But let us take the reverse. If force is known and not xt, the same relation becomes a differential equation. Number of radioactive nuclei of a species is necessarily an integer. For mathematical study, they are often replaced by differentiable continuous variable. Let us next move on to the classification of differential equations. This is simplest example of mathematical modeling often used in ecology, economics, etc. Very simplistic Malthusian model for growth of members, capital N of a species is n dot is equal to A times capital N. A simple predator X, prey Y model translates into the differential equation. X dot is equal to AX minus BY. Similarly, Y dot is equal to CX minus DY. Here, A, B, C, D are the positive constants. This is an example of a system of two differential equations in two unknowns. Let us now move on to understand the classification of differential equations. First one is the ordinary differential equations. If a differential equation involves an unknown function of only one variable, then the equation is called an ordinary differential equation. On the other hand, if it involves partial derivatives of more than one variable, the equation is called partial differential equation. In these modules, we consider only ordinary differential equations. The other parameters of interest are the order of a differential equation and the degree of differential equation. Now, the order of a differential equation is the order of highest derivative that it contains. Degree of a differential equation. It is the power of the highest derivative when an equation is polynomial in all the derivatives involved, including the derivative of order 0. If in a differential equation, ordinary or partial, the dependent variable and all its derivatives occur only to first degree, the equation is said to be linear differential equation. If there is no term containing the dependent variable, it is called the homogeneous differential equation. Now, the examples of differential equations. First, the general ordinary differential equation of order n can be written as f of x, y, y prime, y double prime, and so on till nth order derivative of y is equal to 0. Here, x is the independent variable, y is the dependent variable, and y prime, y double prime, and so on, the nth order derivative of y are the derivatives of y of order 1, 2, and so on till n respectively. Second example, as we have seen in an example above, x dot is equal to ax minus by. Y dot is equal to cx minus dy. We can have a system of differential equations involving one independent and many dependent variables. Third, the differential equation dy by dx plus f of x into y is equal to 0. This is a first order linear homogeneous ordinary differential equation. While if dy by dx plus f of x into y is equal to g of x, this is first order linear inhomogeneous ordinary differential equation. Second order linear inhomogeneous ordinary differential equation example can be written as a d2y by dx square plus k of x into dy by dx plus f of x into y is equal to g of x. Next, the equation dy by dx plus f of x into y square is equal to g of x is of first order, first degree, as the power of the highest derivative dy by dx is 1. But the equation is nonlinear because of the presence of term y square. The equation under root of 1 plus dy by dx whole square is equal to d3y by dx cube is of order 3 because of having the term d3y by dx cube. If the equation is rationalized by squaring it, the power of d3y by dx cube becomes 2. Hence, the equation is of degree 2, which is a nonlinear equation. Next example is of a partial differential equation in 2 or 3 independent variables. The equations can be written as del of phi x of y by del x plus del by del y of phi xy is equal to f of xy. Now we next move on to understand linear first order differential equations. So, the general form of the first order equation is given by y prime is equal to a function capital F of variables x and y. We begin with homogeneous and non-inhomogeneous linear equations. Theory of linear equations is the most highly developed. Most general linear first order equation is given by y prime of x plus p of x into y is equal to q of x. If further in this equation we take q of x to be equal to 0, the equation is called homogeneous equation. Homogeneous equations always have the trivial solution given by y of x is equal to 0. For p of x equal to 0, the solution is given by y of prime is equal to q of x. On integrating the equation, I can obtain the general solution given by y of x, which is equal to the integral of qx dx plus c, where c is a constant of integration. The problem is reduced to a quadrature now, so the equation has been solved in principle. We now discuss linear homogeneous equations. Let us look first at the homogeneous equation y prime of x plus p of x into y is equal to 0. On rearranging the terms, the equation can be expressed in the form dy by y is equal to minus p of x dx. On integrating, we obtain ln of y of x is equal to c minus integral of px dx, where c is the constant of integration. Or the equation can also be written as y of x is equal to k times e raised to power minus of integral of px into dx. This is the most general solution of the linear homogeneous first order differential equation. The trivial solution corresponds to k is equal to 0. This is basically the method of separation of variables, since terms depending on y have been brought to one side and those depending on x alone to the other side. Now, the examples of a linear homogeneous equations includes the Newton's law of cooling. According to Newton's law of cooling, under certain ideal circumstances, a body cools at a rate proportional to the difference between the temperature of the body and that of the surroundings. Thus, if Ts is the temperature of the surroundings, the temperature of the body as a function of time is d capital T by dt is equal to minus alpha times T minus Ts. The equation can also be written as d of T minus Ts by dt is equal to minus alpha T minus Ts. On integrating the equation, we obtain T minus Ts is equal to k times e raised to a minus alpha T. The method provides a family of solutions depending on some constant. One initial condition is required to select a unique solution to the problem. Thus, if t is equal to ti at time t is equal to 0, k is equal to ti minus ts, and t as a function of small t is equal to ts plus brackets ti minus ts times bracket close e raised to power minus alpha t, where small t is the time. Now we consider linear inhomogeneous equation y prime x plus p of x into y is equal to q of x. The corresponding or associated homogeneous equation y prime x plus p of x into y is equal to 0 is called the complementary equation. If y1x is a solution of the homogeneous equation, for the inhomogeneous equation, try solution of the type yx is equal to y1x into ux. Then y prime is y1 times u prime plus y1 prime times u. y1 times u prime plus y1 prime u plus p times y1 u is equal to q of x. y1 times u prime is equal to q of x. So u prime is equal to q of x divided by y1 of x. We obtain on integrating the equation u is equal to integral of q of x divided by y1 of x times dx plus c, where c is some arbitrary constant. Y of x is equal to c times y1 of x plus y1 of x times integral of q of x divided by y1 of x dx. Now, the solution to the homogeneous equation y1x is equal to k times e raised to power minus integral of px dx. So finally, the required general solution of the inhomogeneous equation is given by y of x is equal to c times e to the power minus integral of px dx plus e to the power minus integral of px dx times the integral of q of x into e to the integral of px dx dx. Now we take up an initial value problem. This method of finding the solution is called the method of variation of parameters. Here, first term is a solution of the complementary equation which depends on an arbitrary constant c. This is a general property of linear equations. To any solution of the inhomogeneous equation, we can add a constant multiple of the solution to the complementary equation. The solution contains an unknown parameter. To obtain a unique solution, we must specify one initial value given by y of x naught is equal to y naught. Then the initial value problem will be y prime of x plus p of x into y is equal to q of x, where the initial condition is given by y of x naught is equal to y naught, means at x is equal to x naught, y is equal to y naught, and the problem has the unique solution. Solution is given by y of x is equal to y naught into y1 of x divided by y1 of x naught plus y1 of x multiplied by the integral of qt by y1t dt over the definite limits x naught to x. Now we discuss some examples. First is find the general solution and solution to the initial value problem y of y at x is equal to 0 is 0 for the equation given by y prime plus y is equal to x square times e raised to power minus x. So, p of x is equal to 1 in this equation and q of x is equal to x square times e raised to power minus x. Now, complementary equation is y prime plus y is equal to 0. So, the solution will be y1 is equal to e raised to power minus x. The general solution is y of x is c times y1x plus y1 of x times integral of qx by y1x dx. This is equal to c times e raised to power minus x plus e raised to power minus x times integral of x square dx. Here we have substituted the value of y1 is equal to e raised to power minus x. On further solving equation, we obtain y of x is equal to c times e raised to power minus x plus x cubed by 3 into e raised to power minus x. Now, since it is an initial value problem and the condition is given by at x is equal to 0, y is equal to 0. We substitute the values in our general solution and we obtain the value of constant c is equal to 0. Thus, the general solution becomes y of x is equal to x cubed by 3 times e raised to power minus x. Now we consider another example. The example is to solve the initial value problem y prime plus 1 by x of y is equal to 7 by x square plus 3. The initial condition is defined by at x is equal to 1, y is equal to 0. So first we consider the complementary equation, which is given by y prime plus 1 by x of y is equal to 0. So the solution y1 will be obtained as equal to 1 by x. Solution to the initial value problem, y of x is equal to y0 times y1 of x by y1 of x naught plus y1 of x times the integral from x naught to x q of t by y1t dt. So the equation is equal to 1 by x times the integral of t into 7 by t square plus 3 dt within the definite limits 1 to x. This is equal to 7 by x natural logarithmic of x plus 3 by 2 of x minus 3 by 2x. Next we proceed towards nonlinear equations. Any equation that is not linear is a nonlinear equation. The problem of nonlinear equations is rather complicated. No general methods can tackle all nonlinear equations. Solution to an initial value problem may not even exist, and when it does, may not be unique. For certain classes of equations, general methods exist. Next is the concept of separable equations. A first-order equation is said to be separable if it can be put in the form y of y multiplied by y prime will be equal to g of x. If I integrate this equation, I obtain the integral of f of y dy is equal to a function capital F of y. Similarly, the integral of g of x dx will be equal to a function capital G of x plus c. This is an implicit solution. If f of y is invertible, we obtain an explicit solution. The solution of the initial value problem with y of x naught is equal to y naught will be given by f of y minus function capital F of y naught. This is equal to a function capital G of x minus a function capital G of x naught. Now the examples of separable equations. First is dy by dx is equal to minus of x square plus 1 into y square minus 1 divided by the product of x and y. So the equation may be rearranged as y times dy by y square minus 1 is equal to minus of x square plus 1 by x dx. On integrating the equation, we obtain natural logarithmic of y square minus 1 is equal to c minus x square minus twice of natural logarithmic of x. Y square is equal to 1 plus k times e raised to power minus x square by x square. Second example is y prime is equal to 3x square plus 1 divided by 6y raised to power 5 plus 1. Now the boundary conditions are given by at x is equal to 0, y is equal to 1. So the equation may be rearranged as 6 times y raised to power 5 plus 1 into dy is equal to 3x square plus 1 dx. On integrating the equation, we obtain y raised to power 6 plus y is x cube plus x plus c. This is the required implicit solution. The equation cannot be solved for y in terms of x. Solution to initial value problem is thus given by y raised to power 6 plus y is x cube plus x plus 1. In this here, we discuss the transformation to separable equations. Certain equations are not separable as they stand but can be converted into that form by method of variation of parameters similar to that employed for the linear inhomogeneous equations. Let us consider the example of Bernoulli's equation. Y prime plus p of x into y is equal to q of x times y raised to power n, where n is a real number. For n is equal to 0 and 1, the equation is linear and the methods of linear equations apply. So we assume that n is not equal to 0 and 1. Let y1 be a solution of the complementary equation. So y1 prime plus p of x y1 is equal to 0. We substitute y is equal to y1 times u in this equation and we get y1 times u prime is equal to q of x y1 raised to power n times u raised to power n. The equation may be rearranged as u prime by u raised to power n is equal to q times y1 raised to power n minus 1. Thus, the equation has become separable. Now, the example of separable equations. First is y prime minus y is equal to x times y square. Complementary equation will be given by y prime minus y is equal to 0. So, the solution will be y1 is equal to e raised to power x. U prime by u square will be equal to x times e raised to power x. The equation may be integrated to obtain minus 1 by u is equal to x minus 1 times e raised to power x plus c. Therefore, u of x is equal to minus of 1 divided by x minus 1 into e raised to power x plus c. Or I can say y of x will be equal to minus of e raised to power x divided by x minus 1 e raised to power x plus c. This is the required solution. Homogeneous nonlinear equations. The general first order differential equation is set y prime is equal to f of xy is said to be homogeneous if f of xy can be written as a function of y by x alone. Then the differential equation becomes y prime is equal to f of y by x, which is equal to f of u, where u is equal to y by x. For example, the equation y prime is equal to x square minus xy minus y square by xy is equal to 1 divided by y by x minus 1 minus y by x is equal to 1 by u minus 1 minus u, where y by x is substituted by u. This equation is a homogeneous equation. This definition of homogeneity is very different from the usual notion which we employed in the definition of linear homogeneous equations. We employ this notion of homogeneity only in this section. Now we consider an example. Y is equal to u of x. X times u prime plus u is equal to f of u. The equation may be rearranged as u prime by fu minus u is equal to 1 by x. The equation has been put in the separable form and the solution is given by integrating the two sides. So, integral of du by fu minus u is equal to natural logarithmic of x plus c. Exact equations. An ordinary differential equation of the first order and first degree may be expressed in the form of a total differential P of xy dx plus q of xy dy is equal to 0. If this differential as it stands can be written as a total differential du where u is a function of x, y, then the equation is said to be exact. Its solution in this case is u is equal to c. The necessary and sufficient condition for an equation to be exact is that del p by del y is equal to del q by del x. Now we prove this condition. If the expression above is an exact differential du, then du can be written as partial derivative of u with respect to x times gx plus partial derivative of u with respect to y times gy is equal to p of xy dx plus q of xy dy. Equating the two expressions of du, we have p of xy is equal to del u by del x and q of xy is equal to del u by del y. Differentiate the first with respect to y and second with respect to x and equate the two to get del p by del y is equal to del q by del x. This proves that the condition is necessary. Now, to prove the sufficiency of the condition, we assume that equation del p by del y is equal to del q by del x is satisfied. We define u equal to integral of p of xy dx within the definite limits x prime to x plus w of y. Here, x prime is an arbitrary constant and w an arbitrary function of y. Then u is equal to c will be a primitive if del u by del x equal to p and del u by del y equal to q. If we see the definition of u, the first condition is automatically satisfied. From the second, q is equal to del u by del y, which is equal to the integral of del p by del y times gx within the definite limits x prime to x plus w prime y is equal to x prime integral of del q by del x within the definite limits x prime to x plus w prime y is equal to q of xy minus q of x prime comma y plus w prime y. Therefore, all we require is that wy be given by wy is equal to integral of q of x prime y dy within the definite limits y prime to y. The condition is therefore sufficient for the equation to be exact and it has the primitive integral of p of xy dx within the definite limits x prime to x plus integral of q of x prime y dy within the definite limits y prime to y is equal to c. Now we move ahead with some examples. Let us consider the equation xy dx plus x squared dy is equal to 0. In this equation, p is equal to xy, which gives del p by del y is equal to x, and q is equal to x square, which gives del q by del x is equal to 2x. This is not equal to del p by del y. So we see the condition del q by del x is equal to del p by del y is not satisfied except along the real axis. Thus, there is no region in the plane in which the condition is satisfied. Now we consider another example. The equation is given by 3 times x square y square plus 2x dx plus 2x cube y plus 4y dy is equal to 0. In this equation, p is equal to 3x square y square plus 2x. So del p by del y is equal to 6x square y. Q is given by 2x cube y plus 4y, which gives del q by del x is equal to 6x square y. Here we can see that del p by del y is equal to del q by del x. So to find the primitive, del u by del x is equal to p is equal to 3x square y square plus 2x. On integrating the equation, we obtain u is equal to x cube y square plus x square plus w of y. Del u by del y is equal to 2x cube y plus w prime is equal to q equal to 2x cube y plus 4y. Hence, w prime y is equal to 4 times y, or we can say w can be obtained by integrating the equation. W is equal to 2 times y square plus c. The required primitive is therefore u is equal to x cube times y square plus x square plus w of y, which can also be written as x cube times y square plus x square plus 2y square equals c. In this case, one can solve for y. The solution is y is equal to square root of c minus x square divided by x cube plus 2. The equation is invertible and we get y of x. Let us learn about the integrating factor now. Sometimes the given equation is not exact, so it can be made exact by multiplying by a factor u of xy. This is called the integrating factor. So u of xy multiplied by within the brackets p of xy dx plus q of xy dy brackets close becomes a perfect differential. It is possible that a solution of this equation is not a solution of the original equation, or a solution exists even when the integrating factor does not. However, we will ignore such niceties. Next is the finding integrating factor. If u is to be integrating factor, then the condition of exactness is given by del of up by del y is equal to del of uq by del x, which implies p multiplied by uy plus u multiplied by py will be equal to q multiplied by ux plus u multiplied by qx. In general, this equation is of little value because to find u, we need to solve a partial differential equation, which is an infinitely more arduous task. However, we can try to find an integrating factor which is a product of a function of x and of y if such an integrating factor exists. So let u of xy is equal to v of x times w of y. This implies ux is equal to v prime x times w of y. Similarly, uy is equal to v of x times w prime y. Thus, the exactness condition becomes py minus qx is equal to q times v prime divided by v minus p times w prime divided by w. The situation is even now rather complicated. There exists simple criteria for the existence of the integrating factor, provided we assume it to be a function of only one of the variables. We state the following theorem without proof. The theorem is, let p, q, py, qx be continuous on an open rectangle R. Then, if v is equal to py minus qx divided by q is independent of y on R, then u of x is equal to plus minus e raised to power integral of vx dx is an integrating factor for the equation p of xy dx plus q of xy dy is equal to 0 on R. If w is equal to qx minus py divided by p is independent of x on R, then u of x is equal to plus minus e to the power integral of w of y dy is an integrating factor for p of xy dx plus q of xy dy is equal to 0 on R. Now let us consider an example. We consider the differential equation y dx 2x plus 1 by y dy is equal to 0. In this equation, del p by del y is equal to 1 and del q by del x is equal to 2. We can see that del p by del y is not equal to del q by del x, hence the equation is not exact. However, qx minus py divided by p is equal to 1 by y, which is independent of x. Hence, u of x is equal to e to the power integral of wy dy is equal to y is the integrating factor. On multiplying by y, the equation becomes y square times dx plus 2xy plus 1 dy is equal to 0, which is now exact equation as del p by del y is equal to 2y. This is equal to del q by del x, which is again equal to 2y. Hence, y is equal to 0 is a solution of the modified equation but not of the original equation. Thus, this is a spurious solution. To find the primitive now, we know del u by del x is equal to p is equal to y square. This implies u is equal to xy square plus w of y. Similarly, del u by del y is equal to 2xy plus w prime, which is equal to q and is given by 2xy plus 1. This gives w is equal to y plus c. Hence, the required primitive is u is equal to xy square plus w of y, which in turn is equal to xy square plus y plus c is equal to 0. This can be solved for x in terms of y. X will be given by x equal to minus of y plus c divided by y square. So students, let us summarize what we have learned in this module. With this module, we begin our study of ordinary differential equations. We emphasize the importance of differential equations in engineering, physics, and other branches of science and social sciences and illustrate the same with a couple of simple examples. Next, we classify differential equations into various types. First and higher order equations, linear and non-linear equations, ordinary and partial differential equations, and system of equations, etc. We give illustrative examples of each type. In the rest of this module, we study first order equations only. We first describe methods of solving linear first order differential equations, both homogeneous and non-homogeneous, and provide a few examples. Next, nonlinear equations of the separable type are taken up. We describe a method to convert some equations to separable type. After that, we define what is meant by homogeneous nonlinear equations and give a method to solve such equations. Finally, we introduced the concept of exact differential equations. Some equations that are not exact can be converted into exact equations by multiplying by an integrating factor. We discuss a method of finding the integrating factor in such cases. Thank you.